Hi students, good morning. Welcome back to physics classes. I hope all of you are keeping well, and I think all of you have got your textbook now. All of you have your textbook with you now, and as we complete one topic, the same day itself you have to go through the textbook thoroughly, and the notes now you can make with the help of the slides I am giving here, the description I am giving here, with the help of the textbook. Last year also I told you many times, you have to go through each and every topic related to our syllabus that you mentioned in our syllabus through your textbook. And now all the notes I am in the simplified way I am giving as a slides in the lecture, and that you can refer, and with the help of those slides you refer to the textbook, read the textbook carefully, and you can make your own notes. I think it's not extra points you have to keep there, but every terms and every derivation, every terms I am explaining well in the slides, and the steps are simplified form you can find in the slides. And with the help of these slides, you read the textbook and make your own notes. And remember, all of you keep a copy with you. Not now. For physics, you keep a copy with you. During the lecture, you can note down the important points in a rough paper, and after that, you can revise, and you can again watch the video. It is available there, and you make notes with the help of the slides as well as the textbook. Refer to the textbook. I'm teaching the topics according to the syllabus only. Many times I told you I keeping the lectures along with the syllabus only, means according to the syllabus only. So according to the syllabus, every topic you can find in the video, and the same topics you can refer to the textbook. With the help of the slides, you can make your own notes. And last class I told you about some numerical practices. For that, I'm making another arrangement. I'm solving some numerical examples, and that examples will be sent to you through email from the office, school office. It will be sent to you, and you can refer to those questions that I have already solved. And with the help of those solved questions, the method that we have chosen for solving those questions, you can solve the problems that are given in your textbook. Last year also we are having the same practice. You are keeping another copy for numericals. So all those numericals you have to solve in that numerical copy. So as in the last year, you have to keep two copies for physics. One is for making the notes, and the other for solving the numericals. So topic wise, I will solve the problems and I will send to you, and I will refer some homework for you in that notes that you are getting through email. So follow that also. You refer the solved questions there and try to solve the other problems given in your textbook. Okay, so keep it as take it as in a serious way, because there is no chance now to meet you in person. So this is the only way we have to meet you. Okay, so take it as a serious way, take it in the serious way, and do as directed. Okay, now we can start with our today's session, and we have completed two important topics there. One is electrostatics, that is the properties of charges, and the other is Gauss theorem. So Gauss theorem and properties of charges both are related. That means as a property of charge we have seen electric field and electric field intensity, and Gauss theorem helps you to find out the electric field intensity due to some special kind of charge distributions. So we are sticking back to, or coming back to, the same property of charge, that is electric field. So we have seen what is electric field and what is electric field intensity. So electric field intensity we have defined as the strength of electric field at that particular point in an electric field. So if you want to calculate the electric field intensity, you can either use the Coulomb's law method or Gauss theorem now. But one problem with this electric field intensity is a force acting on unit positive charge. This is a force. Electric field intensity is a force. So force is a vector quantity. So if you are dealing with an electric field, or if you are dealing with the electric field intensity, you are dealing with an vector quantity. What is the difficulty in dealing with the vector quantity? While dealing with the vector quantity, you have to deal with its magnitude as well as direction. You can easily handle with the magnitude, but handling with the direction, it will be a problem. So if you are avoiding the direction aspect of that particular quantity, it will be easy to deal with that particular quantity. So you can't avoid direction from electric field intensity since it is a force, but you can convert that vector quantity into a scalar quantity. You can convert a vector quantity into scalar quantity. So in mathematics, math students, you can learn that how a vector quantity can be converted into a scalar quantity. That is very easy for you, that you will learn in your maths classes. But bio students, you are not going to learn that, but there is a method to convert a physical vector quantity into a scalar quantity. So what is the advantage of converting a vector quantity into an equivalent scalar quantity? So the new scalar quantity will be equivalent to that vector quantity, but it is devoid of direction. So that is the advantage of converting a vector quantity into scalar quantity. So when you are calculating a scalar quantity from a vector quantity, you are neglecting the direction and you are taking a scalar equivalent of that vector quantity. So whatever operations you can do, or whatever you have to do with the vector quantity, that can be done easily with the equivalent scalar quantity without considering the direction. That is the advantage when you are converting a vector quantity into a scalar quantity. So here we are trying to convert our vector quantity, which is that vector quantity, our electric field intensity. You are converting that electric field intensity into an equivalent scalar quantity. How you can convert electric field into its equivalent scalar quantity, and what is that scalar quantity which is equivalent to electric field intensity in an electric field? That is our new topic. And that scalar quantity which is equal to your electric field intensity, which is a vector quantity, is known as electric potential. That is known as electric potential. You are familiar with this term potential. You learned this potential in gravitation. Again, we are coming back to the same chapter, gravitation, in 11th syllabus. There you have defined gravitational potential, which means you are deriving the potential in a gravitational field. Very similar way, here you are defining a potential quantity in electric field. That is why it is called electric potential. So you are defining potential at a point within an electric field. Potential at a point within an electric field. So how you can define potential at a point? So I think you can recollect how you have defined gravitational potential in a gravitational field. So similar way you can define, or you can describe electric potential in an electric field. So I will give you the definition now. Electric potential at a point is the work required to bring a unit positive charge from infinity to the required point within an electric field. I repeat, electric potential at a point, is the work required to bring a unit positive charge from infinity to that particular point. Is it clear? See, the work done in bringing a unit positive charge from infinity to a point in the electric field is called the electric potential at that point. How much work is required to bring a unit positive charge from infinity to a particular point within an electric field? That is defined as the electric potential at that particular point. So electric potential is defined as the work done in bringing unit positive charge from infinity to an electric field. What is work done? Work done is a physical quantity which is a scalar quantity. So electric potential, since you are defining or you are measuring electric potential as the work required to bring unit positive charge from infinity to that particular point, it should be a scalar quantity. So that is why we are saying that electric potential is a scalar quantity. So if you are doing a work, you are not taking its direction, you are just calculating what is the work done against a particular force acting there. So you are calculating the work done as a product of force and displacement, and you are measuring that work done as a scalar quantity. So here, since electric potential is measured as the work required to bring a unit positive charge from infinity to a particular point, you are defining or you are measuring it as a scalar quantity. Okay, so that is scalar equivalent of electric field intensity, that is electric potential. While defining the electric potential at a particular point, that is very important, electric potential at a point is work done in bringing that positive charge from infinity to that point. Suppose both the points are here, one point is at infinity and the other point is in the electric field. So in that sense, we can say what is the work required to shift the charge from initial point to the final point, which is the initial point here, that is infinity, and what is the final point here, that is at a particular point, any point within an electric field. So here you are taking the unit positive charge from initial point which is at infinity. Infinity means beyond the electric field, where there is no potential, there is no electric field intensity. Remember, so electric field intensity or electric potential at infinity will be 0. You always remember that electric field intensity and electric potential at infinite distance or at infinity will be 0. And you are bringing, now here you are bringing the unit positive charge from a point where the potential is 0 to the point where you are finding a potential. So that will be the electric potential at that particular point. Okay, it will be more clear when we are defining electric potential difference. So what do you mean by potential difference? Potential difference, from the term itself, it is clear that it is the difference of potential between 2 points. It is the difference in potential between 2 points. And one more thing you have to remember while you are defining the electric potential difference, both the points are having some potential. Suppose you are having 2 points A and B within an electric field. And A and B should be having their potentials. So what is the difference between these two potential? That is VA minus VB or VB minus VA. That is the potential difference between those 2 points. How you can measure the potential difference between those 2 points? How you can measure the potential difference between 2 points? I will explain. Potential difference between 2 points is the work done to move 1 coulomb of charge between those points. Read it carefully. Electric potential difference, you just now you avoid the terms I mentioned there in volts and units, you have just forget now. Definition, it is that the electric potential difference is the work needed to move 1 coulomb of charge between those points. Now you come back to electric potential at a point. It is the work required to bring a unit positive charge from infinity to a particular point in the electric field. Here, both the points are in the same electric field. Both the points are in the same electric field. And if you are moving a charge from one point to the other, you have to do a work. If you want to move unit positive charge from one point to the other, you have to do a work. How much work is required there? How much work is required there? That work done will be the potential difference between those 2 points. That is the potential difference between those 2 points. Suppose you are moving Q amount of charge. You are moving Q amount of charge. And that Q amount of charge is, to move that Q amount of charge, W amount of work is done. Mentioned there, W is the work required to move the charge between 2 points. The charge moved is Q. So the potential difference delta V, that is the potential difference between them, is given by W by Q. W by Q. What is W? Total work required to bring unit charge from one point to the other. Okay, from that equation you can write W is equal to Q into delta V. What is W? W is the total work done to move Q amount of charge between 2 points which are having a potential difference delta V. Is it clear? We have 2 points. They should have a potential difference delta V, and between those 2 points you are moving a charge Q. For that, W amount of work is required. By the definition of work done, W is equal to Q into delta V. But according to the definition of potential difference, delta V should be W by Q, where W is the work required to bring or to move Q amount of charge between those 2 points. So delta V is equal to W by Q, and delta V is the potential difference. And generally potential difference, electric potential difference, is measured in volts. That is the unit of potential difference mentioned here in red letters, volt. And how you can define 1 volt? 1 volt is equal to 1 joule per 1 coulomb. 1 volt is equal to 1 joule per 1 coulomb. What is 1 volt? 1 volt is, if to move 1 coulomb of charge between 2 points, 1 joule of work is required, then the potential difference between those 2 points is 1 volt. Is it clear? If you are moving 1 coulomb of charge between 2 points, and for that 1 joule of work is required, then the potential difference between those 2 points is measured as 1 volt. That is the definition for 1 volt. So 1 volt is defined as if 1 joule of work is required to move 1 coulomb of charge from one point to the other, then the potential difference between those 2 points is measured as 1 volt. That is the unit of potential difference, volt, and that is the definition for 1 volt of potential difference. Okay, that is potential and potential difference. Suppose you are having 2 points which are having a potential difference 1 volt, and you are moving one electron from or one electron between these 2 points. You are moving one electron between these 2 points. You know, electron is a charged particle. Electron is a charged particle, and you know the charge of an electron. Charge of an electron is yes, 1.6 into 10 to the power minus 19 Coulomb. So you are, if you are moving an electron from one point to the other, you are moving 1.6 into 10 to the power minus 19 Coulomb of charge from one point to the other. And you are moving that charge between or an electron between 2 points which are at a potential difference of 1 volt. How much work is required there? According to the last equation, W is equal to Q into delta V. What is Q here? An electronic charge, that is 1.6 into 10 to the power minus 19 Coulomb. And how much potential difference is there? 1 volt. So how much work is required? 1.6 into 10 to the power minus 19 joule of work is required there. 1.6 into 10 to the power minus 19 joule of work is required to move one electron between 2 points which are at a potential difference of 1 volt. And that particular quantity is defined as 1 electron volt. That is defined as 1 electron volt. So 1 electron volt is a small unit of energy. It is a unit of energy. That unit of energy you will be familiar when you are going to the modern physics. In the syllabus, modern physics, one portion is mentioned as modern physics, and in modern physics you will find this unit of energy as electron volt. So electron volt is a small unit of energy, and it is equal to 1 electron volt is equal to the work required to move 1 electron between 2 points having 1 volt potential difference, and 1 electron volt is defined as or measured as 1.6 into 10 to the power minus 19 joule of work. See, 1 electric volt is the work done in taking 1 electron from one point to another when the potential difference between these points is 1 volt. I repeat, 1 electron volt is the work done in taking an electron from one point to another when the potential difference between these points is 1 volt. So as I already told you, 1 electron volt is equal to 1.6 into 10 to the power minus 90 joule. So from that measure also it is clear 1 electron volt is 1.6 into 10 to the power minus 19 joule. That means it is very small amount of energy. So this is an unit of energy, 1 electron volt, which is defined as the work done in moving an electron from one point to another where 1 volt potential difference is prevailing there. So that is 1 electron volt. Now we have electric potential difference, and using electric potential we have defined 1 electron volt. So we have already defined that electric field is there, and the electric potential is the property of that electric field. And you are defining electric potential at a point as the work required to bring unit positive charge from infinity to that particular point. So we have to define, or we have to find out how you can measure the electric potential at a particular point within an electric field. Electric potential at a point within an electric field. So the simplest electric field that you can find around a point charge. Many times we have considered a point charge as Q or Q0, and we are having a region surrounding that charge as electric field, and at that in that electric field you are keeping a point which is at a distance r from that source charge, and you are bringing a unit positive charge from infinity to that particular point. How much work is required for that? That will be the electric potential at that particular point. I repeat, you are having a source charge. Surrounding that source charge, you are having an electric field. And within that electric field, at a distance r from the source charge, you are finding a point P where you have to find the electric potential. What to do for that? You bring a unit positive charge from infinity to that particular point. How much work is required? That will be the potential at that point. Okay, so we can move on to electric potential due to a point charge. Electric potential due to a point charge. See, in the diagram, you can find plus Q as the source charge, plus Q as the source charge, and you are having an electric field surrounding that source charge plus Q. Are you getting? Don't get confused with the Q and Q0. Earlier I have taken Q0 as the source charge and Q as a test charge. Now here I am taking plus Q as the source charge and plus Q0 as the test charge. So surrounding that plus Q, you can find the electric field. The source charge is providing an electric field. At a distance r from plus Q, see, at a distance r from plus Q, you can find a point P where you have to find out the electric potential. For that, what to do? You have to bring an electric charge from Q0, that is source charge from, test charge Q0 from infinity to that particular point. For that, you consider initially Q0 is at a point A. Initially, that Q0 plus Q0, the test charge is at a point A, which is at a distance x from your source charge. Is it clear? Our test charge plus Q0 now is placed at the point A, which is at a distance x from the source charge. Suppose you are displacing plus Q0 from A to B. When plus Q0 is at A, since test charge and source charge both are positive charges, obviously plus Q0 will experience a repulsive force, and that force is denoted here in the arrow mark. As the arrow mark, the direction of the force is taken in the away direction. But you are moving the test charge plus Q0 from A to B. That is against the force acting on plus Q0 placed at A. Make it very clear, A is experiencing a repulsive force away from plus Q, but you are displacing through dx from A to B, that is towards the source charge plus Q. So you are displacing plus Q0, the test charge, against the force. So you have to do a work against the force on plus Q0 when it is placed at A. Is it clear now? You have to do a work against the force. Now you come back here. At A, which is at a distance x from the source charge source charge q, the force existing F is equal to 1 by 4 pi epsilon 0 q into q0 by x square. No doubt in that, because it is your Coulomb's law. So F is equal to 1 by 4 pi epsilon 0 q into q0 divided by x square, where q0 is the test charge, q is the source charge, and the distance between them is x. And you are displacing from A to B. You are displacing test charge q0 from A to B through a distance dx. And I already told you are displacing it against the force. So according to the force, dx is negative. According to the force, dx is negative. So when you are calculating the work done, dw is equal to F into minus dx. F into minus dx. What is that delta W or dW? That is the small work done to displace the test charge q0 through a distance dx against the force. And what is our aim? Don't forget our aim. Our aim to find out the potential at that point. So as to find out the potential at that point, what to do? You have to bring that charge from infinity to the required point. The required point is at a distance r from the source charge q. So to find out the work done, to bring the unit positive charge you have to bring actually, but here instead of unit positive charge you have taken q0 amount of charge. So to bring q0 amount of charge from infinity to that particular point, how much work is required? To find out that, you can integrate dw within the limit infinity to r. This method we have chosen for many situations. So you already find out the work required to shift the charge through a small distance delta x dx, that is dw. To find out the total work required to move the charge from infinity to r, you have to integrate the small dw within the limit infinity to r. That only we have done here. So the total work required to bring q0 amount of charge from infinity to r, the work done w is equal to integral infinity to r f dx with a negative sign. That negative sign you have taken outside the integral. So what is f here? F is equal to 1 by 4 pi epsilon 0 q into q0 divided by x square. So minus 1 by 4 pi epsilon 0 q into q0. Why these all are taken out? Because all these are constants. Into integral infinity to r 1 by x square dx. You know, integral 1 by x square, many times we have taken this integral 1 by x square, that is minus 1 by x. So you have keeping that constants as minus q into q0 divided by 4 pi epsilon 0 out, then integral 1 by x square will become minus 1 by x within the limit infinity to r. Okay, and here I we have used that many times. You have to omit this negative sign when you are interchanging the limit. So upper limit will become lower limit and lower limit will become upper limit when you are neglecting the negative sign. So it will become minus, or otherwise you can take this minus and this minus you can cancel. Okay, you can, that is better. These two negative signs will become positive. So outside q0 divided by 4 pi epsilon 0, this negative and this negative get cancels. Then you can apply the upper limit and lower limit, 1 by r minus 1 by infinity. Don't get confused. These two negatives are become positive and outside q0 by 4 pi epsilon 0 will come. Then 1 by r minus 1 by infinity when you are applying the upper limit and lower limit. Is it clear? So 1 by infinity is 0. So w will become 1 by 4 pi epsilon 0 q0 divided by r. W is equal to 1 by 4 pi epsilon 0 q0 divided by r. What is this? This is the work required to bring q0 amount of work from infinity to r.
What is R there? R is the distance from the source charge to the required point. So the work required to bring work required to bring Q0 amount of charge from infinity to the required point P is got as W here, which is equal to 1 by 4 pi epsilon 0 Q0 divided by R. Q0 divided by R. Is that potential? It is not the potential, because by the definition, potential is the work required to bring unit positive charge from infinity to that particular point. To find out the potential from W, what to do? You have to divide W by Q0. We have to divide W by Q0. You can remember the definition that we have already mentioned there. W is equal to V into delta V into Q0, where delta V is the potential difference. Okay, the same we have used here. V is equal to W by Q0. When you are finding W by Q0, it will become 1 by 4 pi epsilon 0 Q by R. What is that? That is the work required to bring unit positive charge from infinity to that particular point. It is the work required to bring unit positive charge from infinity to that particular point. By the definition of electric potential, that is equal to the potential at that particular point. By the definition, that is the work required to bring unit positive charge from infinity to that particular point, and that is the electric potential at that point. Is it clear? Go through the steps. Nothing we have done. We have initially find out the force acting on Q0 when it is placed at A, and it is displaced through dx against the force. For that, a work is required dW, which is F into minus dx. Then to find out the total work done to bring it from infinity to R, W is equal to minus infinity to R integral F dx. Then you substitute for F. Then take out the constants out of the integral sign. Integrate 1 by x square. That will result to you minus 1 by x. Apply the limit, upper limit minus lower limit, and you will get the total work required to bring Q0 amount of charge from infinity to R. That is not the potential. To find out the potential, by definition, it is the work required to bring unit positive charge from infinity to R. So you divide W by Q0. So you will get V is equal to 1 by 4 pi epsilon 0 Q by R. So due to a point charge Q, at a distance R, the potential, electric potential is given by 1 by 4 pi epsilon 0 Q by R. 1 by 4 pi epsilon 0 Q by R. What is electric field intensity there? At a distance R from a point charge, electric field intensity is given by V is equal to 1 by 4 pi epsilon 0 Q by R square. Electric field intensity is equal to 1 by 4 pi epsilon 0 Q by R square. But electric potential is equal to V is equal to 1 by 4 pi epsilon 0 Q by R. What makes the difference here? Electric field intensity is a vector quantity, but electric potential is a scalar quantity. Both are equivalent to each other, but they are not equal. Remember, they are not equal, but they are equivalent. So, electric field is a vector quantity and its equivalent scalar quantity is electric potential. So here the test source charge that you have taken is plus Q. So you have got the potential V is equal to 1 by 4 pi epsilon 0 Q by R. Suppose instead of that plus Q charge, as that source charge you have taken minus Q charge, negative charge, then what will be potential? Don't worry, the potential is V is equal to 1 by 4 pi epsilon 0 minus Q by R, or we can say that minus 1 by 4 pi epsilon 0 Q by R. So in a positive field you can have the potential as positive. In an electric negative field, then you can find the electric potential as a negative potential. So positive potential is denoted as 1 by 4 pi epsilon 0 Q by R. And for a negative charge, test charge, V is equal to 1 by 4 pi, minus 1 by 4 pi epsilon 0 Q by R, or 1 by 4 pi epsilon 0 into minus Q by R.
So that is positive potential and negative potential. Suppose here we have find out the potential due to a point charge. Suppose instead of that you are having an electric field of a combined system of charges. That means many charges are there and each charge can provide a potential at that particular point. Are you getting that? We are having a system of charges and we are having a point P within the combined field of all these charges. And what will be the potential at that particular point? That we have to find out. That is electric potential due to a system of charges. Electric potential due to a system of charges.
See, here you are having 4 charges. You can find plus Q1, Q2, Q3 and Q4. Charges Q1, Q2, Q3 and Q4. Q1 and Q2 are positive charges and Q3 and Q4 are negative charges. Q1 and Q2 are positive and Q3 and Q4 are negative. P is a particular point where we have to find out the potential. And P is at a distance R1 from Q1, R2 from Q2, R3 from Q3 and R4 from Q4. P is a point which are at a distance R1, R2, R3, R4 respectively from Q1, Q2, Q3 and Q4. And we have to find out the potential at P. Listen, Q1 can provide a potential at P. How you can find it out? By the definition or by the equation P is equal to 1 by 4 pi epsilon 0 Q1 by R1. Q2 can provide a potential there, that is measured as 1 by 4 pi epsilon 0 Q2 by R2. We are having Q3 at a distance R3, so at P Q3 can also provide a potential. V3 is equal to 1 by 4 pi epsilon 0 Q3 by R3. Similarly by Q4 1 by 4 pi epsilon 0 minus Q by R4. Remember, potential provided by Q1 and Q2 are positive and provided by Q3 and Q4 are negative. How you can find out the total potential at that particular point? To find out the total potential at that particular point, you have to add all these potentials, individual potentials. So in all the terms 1 by 4 pi epsilon 0 is common. So to find out the total potential V, you can take 1 by 4 pi epsilon 0 as common into Q1 R1 plus Q2 R2 minus Q3 R3 minus Q4 R4. There is no chance of any confusion. We are adding the individual potentials provided by Q1, Q2, Q3 and Q4 respectively. Among them Q1 and Q2 are positive since Q1 and Q2 are positive charges, and the potential provided by Q3 and Q4 are negative since they are negative charges. So the total potential will be V is equal to 1 by 4 pi epsilon 0 Q1 R1 plus Q2 R2 minus Q3 R3 minus Q4 R4. Okay, so in sigma notations you can express it as V is equal to 1 by 4 pi epsilon 0 sigma I varies from 1 to n Qi Ri. You can apply that into the above case where n is equal to 4. So I varies from 1 to 4. So the first term 1 by 4 pi epsilon 0 will remain there. First term will be Q1 by R1 plus Q2 by R2 plus Q3 by R3 plus Q4 by R4. But remember, when you are substituting Q1, Q2, Q3 and Q4, you have to consider their nature also. Q1 and Q2 are positive and Q3 and Q4 are negative. So this is a simple expression so as to find out the potential due to a system of charges. Again, it is your superposition principle. It is superposition principle. So electric force, electric field intensity and electric potential all obey superposition principle. This is potential due to a system of charges. In general, total potential is equal to 1 by 4 pi epsilon 0 sigma I varies from 1 to n Qi divided by Ri. Remember, while you are taking Q, you have to take in account their nature also. Okay, so that is electric potential difference
using these concepts, we have defined a unit of energy as electron volt, and we found electric potential due to a point charge and a system of point charges. So we have defined an equivalent scalar quantity for electric field intensity, which is defined as the electric potential, which is the work required to bring unit positive charge from infinity to a particular point. If you are defining electric potential difference, that is the work required to move unit positive charge from one point to the other. And both are the work done, they are scalar quantities, and electric potential is a scalar quantity. So that's all for today. We will meet again. Bye.